Okay, now just now we stopped at these slides where just now we mentioned that our T star transform matrix here is not in a square matrix. So now we need to have some treatment, or we need to fix this. We need to put our transformation matrix here into a square matrix, where it will fit into our case here. So we need to build from 4 times 2 matrix like this into 4 times 4 matrix. So what are the steps here? Yeah. Okay. Now recall our displacement matrix on a displacement matrix T equal to transformation matrix and the T. So our displacement on the left is again is a local dimension. Right hand side is a global dimension, and we have seen this before for the transformation matrix. C as C again, each one of it referring to their respective location, which is U1, V1, U2, V2. That's why we see 0, 0 here, because the first equation we don't have U2, V2. Second equation we don't have U1, V1. We only have CS here. So we need to transform into a more complete equation. So by adding U1 prime, by adding this one, and U2 prime, because on the left hand side here we only have the x direction, yeah, because the equation just now we only have the u is x direction only. Where's y? Y is missing on the left hand side equation. So on the right hand side, displacement is quite complete, but we are missing some component at below here. So something missing here. So we need to convert the known equation that we see just now into a more complete one with the V1 prime and V2 prime. Just call back the equation that we derived earlier this morning. So you just put in accordingly. Yeah, just put in accordingly. V1 prime equal to negative sine V1, right? This one, how we get negative sine and cos here? You recall back in the previous slide with this when we do transformation with this one. Let me see. Okay, yeah, this one. So recall back this equation. And just now, this equation was missing in our matrix. So U1 equal to negative U sine theta plus V cos theta. We put this matrix back into the matrix. Yeah. So that's why we will have this one. Okay. So again, we rewrite the equation into a more complete form where we will have 4 times 4 matrix. This is 4 times 1 matrix. So here we will, if you time these two, you cancel the middle one, you'll get 4 times 1. So that's why you have 4 times 1 matrix on the left. Okay. All right. So Lai, you understand why suddenly there's a minus S here and minus S here. Lai, you understand?
Okay.
You understand?
Okay.
You okay means you understand, right? Okay. All right. So in this case, we have our transformation matrix in a more complete form. We can write d prime equal to t d. So your t represent this 4 times store matrix. Again, we will see 0, 0 on the right hand corner of the matrix and 0, 0 at the left corner of the matrix. Yeah. Again, this is U1, U2, V2, U2, V2 column. Okay, so you just need to fill in the blank accordingly. Then you'll see. So we have 4 equations here. These 4 equations we get from the previous slides. So yeah. So why we have 4? Because we have 2 points. Each point give you 2 displacement. So we have 4 displacement. Okay, quite straightforward for these slides. Yeah, this is just a rewrite the term here. So again, when we derive the displacement transformation matrix within the 4 times 4, we can do it the same for the force also, using the same transformation matrix here. F prime equal to T force. Right? Again, on the left is a local, on the right is global. What I mean by local is the prime axis, which is the yellow color in the first slide that we see this morning. Yeah, the yellow color axis, and then the global on the right means the blue color axis that you see, or XY axis. Okay, so today what is important is that the transformation matrix between local and global, you can use this transformation matrix 4 times 4 matrix. You need to know that on the left is local, on the right is global. Then you can use your transformation matrix in this form: CS minus SC, CS minus SC in this form. So the location is fixed already. So in the exam, some parameter will be missing, and then you just solve your matrix solution. All right, you just solve for the matrix equation. So again, how to solve a question in the matrix form? Open up the calculus textbook or advanced mathematics textbook for the matrix chapter. Okay, go and look at how you solve for matrix. Yeah, so I think if you did your STPM, then you look for the STPM advanced mathematics. Or if you do diploma or you do SPM, this one also cover. But SPM doesn't cover up to 4 times 4. You need to look up to calculus, where we have a 4 times 4 matrix. Okay. The next will be, we need to call in the bar equation again. So we are looking at bar scenario. So F equal to KD again. So again, our K here is a bar, so we need to convert our K in a term of AE over L times the displacement. And when you see the prime, it means we're looking at the local axis, right? We're looking at the local axis. And a fixed idea, in this case, if you want to use the transformation matrix, your object must be on local axis. The object must align with the local axis with the prime, and then you look at what is your global axis data, like that. Okay, so it's important. So it will be different if your object align on a global then you need to convert into local, then it will be different. It will be different case. So again, don't confuse with these two. As long as you know the structure of the equation, when you do conversion, just recall, use everything in a general term here, and then only focus left-hand side is the local, right-hand side is a global. So what you see on the photo, you just put according to their location. So yeah. So maybe I'll give you a small illustration, transformation, and for like that. So if you need to use this equation for both cases, so on the left, normally you will have all the force in the left-hand side because all your local, the bar is aligned to the local, so you fill in all the data from the left. But if your question, exam question, give you your bar was aligned to the global, then you start filling in your data in the global first. Then you solve from here. Then you can find your f prime in this equation. Okay, so you just use the same equation, only you look at the diagram or look at the problem, and then you just fill in the known data first, the given data, in the correct location. So if your object aligned to the local axis, means you have data along the local. So you just fill in the local on the left, then you solve. Transformation matrix fixed already. You don't need to change, it's fixed already. So you have these two, you're able to find this one, right? So same with this one. If your object align with the global axis, then you fill in the global axis data. You do the transformation over here, you will get, you do the matrix solution, transformation, this matrix times this matrix, you'll get answer right here. Okay. So again, previously we only cover for x direction. What about y? Y is missing, so you need to fill in, and you put in the more complete form. Meaning, if you refer to the diagram on the left here, you have 2 points. Each point have two direction. So this is the first point. First point give you f1x and f1y. Second point give you f2x and f2y. So, and then you have a 4 displacement. So yeah, so 4 displacement, why we know that we have 4? Because each point have 2 displacement. So we have 4 times 1. So matrix you must have 4 times 4. Okay, because on the left here you have 4 times 1 matrix. So how you determine the size of your matrix is that you re-engineer the matrix format. So if you take 4 times 4 times the 4 times 1 matrix, the product will be 4 times 1. Yeah. So this is a fundamental mathematics for matrix solution. Yeah. Okay. And yeah, so again, you see the transformation matrix a little bit different from the previous one. In this case, we will have 0, 0 here. Why? Because we don't have y. In this diagram, we don't have y force. We only have x direction force. So if you have y direction, then you have something inside here. So you need to derive the equation also, yeah. So this is just a direct explanation by using the diagram on the left. Yeah. So not necessary every time if your bar have two forces. So for example, we have pulling force in x direction, pulling y in y direction. If you have external force in x and external force in y direction in this point, then they will not be zero here. In this case, you only have one direction force. Yeah. So just a reminder or side note for that one. Okay, let's see if we have an example. So again, F equal to KD, your K in this form, yeah? So just now we look at F transformation matrix. This is F, K, and D, yeah? FKD. So don't confuse between the transformation matrix and the stiffness matrix, yeah? So we have two types of matrix here. Just now, what we discussed so far, this one, what you see on the screen here is, what you see on the screen here is transformation matrix, yeah? The CS minus XC 0, 0 and CS minus XC 0, 0 on the left. This one is transformation matrix because you're looking at displacement and displacement, right? Displacement and displacement. Transformation matrix deal with the conversion between the same entity, means displacement to displacement, force to force, stress to stress. However, the fundamental that we learned since chapter 1, the F equal to KD, this one is what we learned from chapter 1, F equal to KD, and this one. So we need to convert this one into a more complex form. So you will have a complex matrix look like this. Yeah. Again, just to remind you, this matrix form only works from the diagram on the left here, where you only have a direction on the x-axis. So again, if your bar is having y component, which is you are pulling from y and x, when you have fx and fy, then there's a value inside here. You need to derive the equation, yeah, for each point. So again, your K prime, you can rewrite as AE over L in this form. So you will see your K equal to AEL and 1, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 1, 0, and 0. Okay. Okay. Maybe just a little bit more explanation. So again, this is x direction only. How about y direction? So how you fill in the matrix? Again, you write U1, U2, U1 V1, U2 V2. Okay. Okay. So just be careful on the arrangement of your data. So don't write in this form. So if you write U1, U2, sometimes it's difficult to explain the wrong answer. U1, U2, V1, V2. If you write like that, this is wrong. This is wrong arrangement. You have to write the first set for point 1. So point 1, you have U1, V1. And then you continue with point 2. So point 2, you have U2, V2. Don't mix up between all the points. So don't write like this on the top hand corner that I write just now. Okay, again, you arrange your data based on point. So point 1, you have U1 and V1. Point 2, you have U2, V2. So be careful on the arrangement for the location. Okay. Okay, so again, we look at transformation. So D equal to transformation D, so displacement, force to force, right? Displacement to displacement, force to force with the same transformation. We need to substitute, then we will get this form. Okay, we need to use this these two equations to convert what we have. So this side is what we learned on the transformation. It is the displacement to displacement, force to force on the transformation. And this is what we learned from the Hooke's law, F equal to Kx, or F equal to AE over L, or F equal to KD, like what we learned so far. So we want to see how the transformation done by using the T and K. So again, you substitute this one. Okay, let me erase a bit messy. This one, you substitute over here. This one, you substitute here. Okay, you use the F equal to KD matrix equation, and you use the transformation matrix equation. Substitute, you will get this equation. TF equal to K prime TD. Katana, you understand how we get this equation?
This substitution.
Yeah, correct. It's just a substitution, yeah? Okay. All right. How you cancel the matrix in this way? So again, this one you need to flip back your calculus. How you cancel the matrix on both sides? You need to times, okay, matrix A times its own transpose or inverse matrix. You will get identity matrix. This one, what is identity? You need to refer to appendix A, or again go back to your calculus matrix chapter. Yeah. So you cancel both sides by multiplying T minus 1. So T minus 1, you cancel out the T. Yeah. You cannot just cancel like that. You need to times both sides with inverse matrix. Okay. This is just a strategy in mathematics. So again, how to do inverse matrix? Go back to your calculus chapter. Yeah. So when you time both sides with T minus 1 or inverse matrix, so this side cancel, you only have K prime T, and this side you have T minus 1. T minus 1. Okay. So another add-on information here. I'm not sure whether we have time, but just an add-on information that our inverse matrix T minus 1 is equal to our transpose matrix here with a T here. So again, what is transpose matrix? Refer to appendix A, or your calculus textbook. What is transpose matrix? right? We don't have time to cover the mathematics part. So you need to call back what you learned in your advanced mathematics or calculus 2 program. Yeah. So there's an equation that link inverse matrix and transform matrix. So both of them are equivalent. So if inverse matrix will be equal to a transpose matrix. Yeah. So again, it will be your homework for today or this week. Go and refresh what is transpose matrix. How to do transpose matrix. Yeah. 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 Again, go and see appendix A. So we can write F equal K prime T, and just now we say that T minus 1, which is your inverse matrix, is equivalent to a transpose matrix. Yeah. Again, the steps was shown in appendix A. How do you do transpose? Or you can go more detail in your calculus textbook or advanced mathematics textbook. Yeah. So this is a general idea how we solve problems. Yeah. Okay. What else we trying to do here is that just now we link up the middle one, the matrix in the middle one with the transpose matrix. So again, call back the earlier we learned the F equal to KD. So we try to learn, try to link our K matrix with the K prime matrix and T matrix. It means that we are trying to find the relationship between the local identity, local data and global data. So the equation that you see on the screen on the top here is a local data with the prime, and then the lower one is more on the global dimension. Yeah. So you can link these two, the matrix dimension together. So your K equal to K prime T and T transpose. So by having said that, you can do a conversion by on the matrix, on the stiffness matrix itself. Then you solve for the force and the displacement in the equation. Okay, so this is a very important equation that help you to convert from one dimension, from local to global. And this one, we look at the stiffness matrix dimension. All right. K equal to K prime T times T transpose. You will get your global matrix. Yeah. It will be a very lengthy calculation for T transpose and T. Again, go and look into your advanced mathematics or calculus textbook. Yeah, how to do transpose. We don't have time to cover for mathematics component. Right. So just a review. Just now our transformation matrix. Again, transformation matrix is only used to convert the same component. For example, convert displacement to displacement, means local displacement to displacement. To convert force in local to convert between force in local to force. Yeah, these two lah. Huh? So the same dimension or same means displacement, force and force. you use transformation. It's a conversion factor there. So here, again, when you see T, it means you're only converting the same, what is the word that I should use? But the idea is just that if you look at the transformation T here, means you only convert displacement, force to force, or stress to stress, means the same physics parameter. Okay, yeah. So again, if you see 4 times 4, you know that this is 0.1, this is 0.2. So 0.1, you have y and x direction, u1, v1, u2, v2. Yeah, so start practicing this kind of node side node. Yeah, so this is again 0.1, 0.2. So you have u1, v1, u2, v2. Then it will help you to fill in the correct numbers here. T just now, K also we learned. The K prime equal to AEL and all the parameter inside there. And again, we're looking at 0.1, 0.2, U1, V1, U2, V2, same. So all this we derive from our equation. So we put our K means that you use this equation. You put in transpose here. You put in your K. Over here. And then you do T transpose for this matrix here. Now, how to do, you need to refer to the textbook because it's quite a lengthy process. Yeah, you need to move here and there. Okay. Yeah, go and learn how to do transpose. Yeah. Yeah. So because this one is a mathematics chapter, we don't have time to cover. Yeah. I wish to go, but we don't have time. Yeah? So once you do all the mathematics conversion, again, go and do your homework. Learn how to convert this matrix into transpose. How to do T transpose or matrix transpose. How to do this one. Yeah, go and learn. Yeah. So when you do the matrix calculation, at the end you arrive at the one that you see over here on the screen here. So you will get K equal to AE, and you have C square CS minus C square minus CS, S square minus CS, minus S square, C square, CS, S2, and here will be symmetry. Yeah. Okay, what mean by symmetry? It means it's a mirror. So we just want to save time. Sometimes we are lazy to write on the bottom here. So we will use a symmetry words here. It means what you see, this is your mirror axis. So what you see here will be reflected on another side. So means this one will be minus CS. You're reflected directly, yeah. So if you do not know what is symmetry matrix, go and look into your calculus textbook also. Yeah. Okay. So another new matrix today, which is K equal to AE over L with your cos and sine inside there. And this one, we only look at X and Y plane. Yeah? Okay. So again, if you have many, then we will add up all the metrics together. We will see this equation later on with one example. Same with the force also. Yeah. Okay, we look at one example, then we call it a day. Yeah? Okay, so this equation, this example is available in your tutorial question handout. This will be in your this one will be in your question number 9. Yeah. So will be question number 9, correct? Question number 9, tutorial question. So again, we will have one bar on the screen here, and this bar was located in the local axis, x prime. And the angle between the global and local is 30 degree. So the statement was given as follow. So you need to evaluate the global stiffness matrix with respect to x and y coordinate system. Let the bar cross-section area A equal to 2 meters square, length equal to 60 meter, so L equal to 60. Modulus of elasticity, which is your E, equal to 30 megapascal. All right. The angle of the bar marks as 30 degree, like this. So how do we find the global stiffness matrix? So again, since we are given the angle 30 degree, and this is quite similar to what we have in our lecture just now. So we do the conversion of the unit first, because we need to, you know that when you deal with the global stiffness matrix, you know that you deal with cos and sine. Okay, so cos 30 equal to square root of 3 divided by 2, and sine 30 equal to half, or 0.5. Yeah, 0.5. So you can use your calculator to use the decimal one, or you can just use the simplified format in the fraction form. Okay, so this one also in the trigonometry chapter. But I will encourage you to memorize cos 30 equal to this form, sine 30 equal to this form. You'll be better when you do your calculation, because sometimes you can cancel out, or you can factor out the half here. Yeah? So again, recall what is the stiffness matrix that we derived just now. The K equal to 8 divided by L with the symmetry matrix here. C square CS minus C square minus CS and so on. Yeah. So how you memorize is that you draw a diagonal line, and then we start with the C square S square C square S square, and then you continue with the second diagonal line, CS minus CS CS, and then the third diagonal line minus cos square minus S square, and then the last number minus CS. So, and then symmetry means you mirror, you copy what is reflected to another side. Yeah. So means over this side is the same like this one, but reflected. Yeah, reflected to this side. So you copy or you substitute all the value. A is 2 meters square, so A is 2 here. E is given 30 megapascal, so you write 30 times 10 power 6. L is 60, so 60. Again, when it comes to test, my favorite is that I will change the unit inside here. Remember to change to unit SI. Yeah. So again, remember to change to unit SI during your test or final exam. Okay. It has been a standard approach to test your awareness in exam. Most of the time, you will see cm or mm over here, and this one will be mm square, and so on. So remember, when you do calculation, change all the unit to unit SI before you you do, yeah. So and the rest is just do the normal calculation. For example, c square cos square means you square this one, you will get 3/4. Get this one. Cs, you take cos times sine. This one times this one, you get square root of 3/4, and so on. Yeah. So this one is just your a reference answer for during your revision. So the rest is just substitution of the numbers. Okay. And then we just simplify to this one means you times in all the you do the calculation, yeah. So 10 power 6, and then this one you convert lah in the more simple form. So this is the answer. Yeah, this is the answer. So in exam, don't stop at here. You have to give me a more simpler answer without the division here, without the fraction number here. Okay. And outside the matrix, only a more simpler form, 10 power something, yeah, or a common factor of all this number. Yeah. Okay, now in test, don't stop at this stage. Give me a more simpler answer, like this one. Okay, you can factor all the 1/4 outside, and then give me a more simpler term here also can. Yeah, just that don't give me the fraction number here. Okay, and the unit is Newton over meter. Yeah, you know that your stiffness matrix always in the Newton over meter. Okay, so any question for this tutorial question? Anything that you want to ask me? If no, then I stop the recording.